everyone. Welcome to Cohere for AI Technical Talk. Today, we have a team of speakers. So we have Dustin Tran, Jeremiah, Liu, and Mike Dusenberry. They are going to be talking about Plex, which is a recent paper by their team from Google Brain that explores how to make deep learning more reliable while keeping good performance in many tasks ranging from vision to NLP. Our team of speakers is truly amazing. We've got people who have been, we've got Dustin, who has worked at Stan, and Edward 2, and many other extremely important probabilistic software. We've got Mike and Jeremiah, who have done some also truly interesting work on Bayesian learning and bringing that through the era of deep learning. And I'll leave it to them.
All right, thanks, João, for the intro. Yeah, it's great to present. And yeah, thanks for inviting us. So we'll sort of just go through an overview of Plex. If you have questions, definitely feel free to raise them, I guess, in Zoom, and we can sort of answer them off the cuff. But otherwise, we'll also leave a ton of time for questions at the end. Okay, let's get started. So this is a joint effort from our team within Google, as well as a collaborative effort across a few different like orgs within Google and some external labs, so in particular, Yarn Gall's group from University of Oxford. And there's a bunch of links here that you can feel free to check out. So the core goal of our work is really this as follows. We'd like our models to be reliable. So what do we mean by reliability? It's to have a model that performs well consistently over a large collection of decision-making scenarios. So there's been many advances across different facets of uncertainty robustness, areas that I'm quite passionate about or we're quite passionate about. However, what I found is that papers in these areas have largely been hyper-optimized toward their own problem setting. And I find that kind of unfortunate. That's led to sort of a fragmentation in literature where it's sort of unknown how well ideas transfer across the larger problem these papers care about. So for example, do techniques for calibration transfer to out of distribution detection? These are two very common settings for using uncertainty or querying unsafe predictions. Do techniques in robust generalization and robustness translate to free-shot learning or free-shot? So I think these papers making specific advances are great, but I think they largely ignore this overall bigger picture, and I think that's this one about reliability. So to set out towards reliability, what we did was we sort of started from like a bottom-up perspective of like thinking about the foundations of what are the key desiderata toward achieving the like broad performance goal. So on one side, what we care a lot about is robustness. So we want models to have strong predictive performance. Okay, so that was an interruption. So we want models to have a strong predictive performance across a large set of distribution shifts. So what we're showing you here is just a few different examples. So, on your in distribution, like your typical test set, that's usually like a split from your training sets. You want to, have models generalize to that unseen data. Under covariate shift, it's a type of distribution shift where your input distribution changes. You like to generalize well. There's also subpopulation shift where you care about different parts of your overall population. Really, this is all about just having generalizable predictions. Okay, and the second sort of pillar, what we care a lot about is having models that not just predict well, but they should know exactly whether their predictions are good or not. So they can do sort of a self-evaluation sort of process. So here, predictions are part of a overarching decision-making scenario where the models are really sort of just actions in a larger system. Typical examples like human model collaboration or like selective prediction. Another example is open set recognition. So you can sort of flag inputs that your model can tell whether like an existing sort of input is supported or not. So a common example of this is like your models for a hotel service and you're trying to book flights, and you ask it to like book a taxi or something. It's just something completely, that the model, a service that the model doesn't support, or in an assistant scenario or dialogue sort of scenario, the model doesn't support it. You like the model to just not have garbage input, garbage output. You should have the model explicitly just, ignore the, or just say it doesn't know. One final uncertainty task I think is also important here, that's sort of been underexplored, is known as label uncertainty. So this is sort of uncertainty inherent to the overarching, the overall data. And this is sort of irreducible uncertainty. It's uncertainty caused by measurement error. So as you collect more and more data, you'll never be able to exactly reduce that level of uncertainty. So we like to capture the full sort of distribution of uncertainty that comes from, say, rater ambiguity, when you're sort of like crowdsourcing labels and there's an inherent sort of noise around that sort of labeling process. And finally, I think another important area is having models that not just perform well sort of in static sort of train test splits or train OOD splits, but you'd like models to sort of perform well across its overarching learning process. So the most common setting that people are familiar with is few-shot learning. So you're doing this over, just acquiring a few different examples and then generalizing well just from that a few examples in the task for a given task. I think an area that's also been sort of explored in the traditional literature, but hasn't been recently, sort of known as active learning. So here you're not only learning from a few set of examples, but you're also sort of participating in selecting the specific examples that you can learn from. And finally, I think uncertainty in this area, this overarching area, is also extremely challenging. These are areas where the data is also is generally quite small. So these are precisely the areas where I think having models that know what they don't know is like especially critical, because they're just more likely to be incorrect. So this is broadly the full desiderata for what we're calling reliability. The goal here is to test a single model sort of out-of-the-box performance across the full suite of benchmarking across tasks here. And this is having one model that can do this without any sort of customization for individual tasks. And I'll let Mike take it away, I guess, to talk about Plex, the model.
Yeah, thanks, Dustin. Yeah, so with that, I want to introduce our paper on Plex, where we really try to push on this reliability goal that Dustin just discussed using what we call pre-trained large model extensions. All right, so let's jump right into the setting, and we'll look at the data sets, models, et cetera. Dustin, you want to go forward one? All right, so for this paper and like all this work that we're going to discuss, here's like the general setting. In all cases, we're going to start by pre-training a model on some large data sets. It's maybe JFT or C4. We'll talk about those. Following that, we're going to fine-tune the model on maybe ImageNet or NowU, et cetera. And then we're going to evaluate them on a suite of data sets for the tasks, looking at these different aspects of reliability that Dustin discussed. And then occasionally we'll also present results going straight from a pre-trained model directly to evaluation. Example there is like zero-shot out of distribution detection. So this kind of general framework. With that, let's talk about data sets and tasks. So in the paper, we look at kind of two modalities, vision and language. So we'll start with the vision one. So yeah, kind of high level here, it's what we just said, pre-training, fine-tuning, eval. For vision, we always pre-train on JFT or ImageNet 21K, and JFT goes up to 4 billion images. We're going to fine-tune on ImageNet, CFAR, Retina, which is a diabetic retinopathy data set, places 365. And then eval is where we really get into this like evaluation framework for reliability. And this we're going to have a set of data sets. They'll correspond to the data set that we fine-tuned on, looking at different aspects. So one example is for covariate shifts, or kind of like shifts in the inputs where we still aim to map those to a certain set of classes that we trained on. We have a whole suite of ImageNet data sets that have existed in the literature. So for example, ImageNet C is like corrupted or noisy inputs. ImageNet A is adversarial inputs. ImageNet R is like artistic renditions of inputs. V2 is a more difficult test set. And the other two ones there are based on videos and looking at like difficult frames around some anchor frame. So all those are gonna let us understand how robust our model is to changes in the inputs. And we're gonna have like analogous ones for retina and CFAR and et cetera. One other example here is, so Dustin mentioned label uncertainty. Usually in the data sets we have, right, we're going to have maybe just one hot encoded labels for each example. But in these data sets, ImageNet Real H and CFAR 10H, they're interesting because they were created as evaluation data sets using a set of human annotators. And that set of human annotators may disagree on the label for a given image. And thus, you can identify their collective set of labels as a distribution over labels. And then we can look with that at how well our model's uncertainty, predictive uncertainty over the labels matches up with a set of human annotators. We're also going to have OOD data sets. So we might fine tune on CFAR 10 and then try to evaluate maybe a close, near or far OOD by saying a CFAR 100 out of distribution or SVHN, et cetera. And we may also do those in a zero-shot setting, like I mentioned. And we have other ones as well for adaptation, subpopulation shift, et cetera. All right, let's talk about the text ones then. So as the other modality, we have language. And again, we have pre-training, and I've kind of mixed together the fine-tuning and eval as the tasks section. So pre-training, all our models in this paper are going to be on C4, so the cleaned up common crawl data sets. We're going to use T5 checkpoints for the language. And for tasks, we've got three different language tasks. One is natural language inference, so just does some sentence entail another sentence. We'll use the multi-NLI data set for that. Next one is toxic comment detection. We'll use Wikipedia talk for that. And the last one I think is interesting, it's natural language understanding. And we'll actually propose a new data set as a combination of a few existing data sets, which we'll call NowU. But in this one, we actually want to take in a sentence and then output a structured output of 3 tokens, where each of those tokens comes from some number of classes. In particular, we're going to take a sentence and maybe say, classify this into some vertical, which is like some kind of general topic or category, then some domain, which is maybe some like more specific subdomain of that vertical, and then some intent, like what does the user want to do? What's interesting, what we'll show later is by doing this, we can kind of do things where like, the model can actually say, well, I understand the vertical you want, I understand the domain, but I don't understand the intent and I don't support that. But and so maybe I can like, route you very quickly to some expert, or in some system, you could route up to some expert model. So given those 3 tasks on the table there, just the first column is the in distribution, and the other columns are these like shifted or out of distribution data sets for those respective tasks. All right, now let's look at the models. So base models, we're going to put things on top of these, but what do we start out with? So for vision and text, we're using transformer-based models. So vision, that's a vision transformer. We're look at large, base, and small sizes, and our main results will be on large, specifically the L32 version. And for text, these are T5 models. So again, large, base, and small, and our main one will be the large size model. All right, and so then what do you come to Plex? Like, what are the overall key ingredients from the modeling side? So we would say there's kind of 3 categories of ingredients. One is this kind of like idea of large scale pre-training, right? This is very common now. So tree training on JFT, like I said, or C4 for text. We think pair that with a transformer-based architecture. So we just said vision transformer for vision, T5 for text. And then importantly, we add these model extensions. So we have 3 such extensions. We'll talk about where exactly we put these. One of them is batch ensemble, so trying to get the benefits from ensemble, but a little bit more efficiently. The second extension is replacing the last layer of the model with a Gaussian process last layer to get a little bit better estimates of uncertainty and awareness of in distribution versus out of distribution. And the third extension is replacing the last layer again with a heteroscedastic layer, which allows us to get a little bit better estimates of the label uncertainty that we talked about. So I just want to do rapid fire through each of these very quickly, and maybe have so there's a little bit pointers of what to look into if you want more details. So let's go into the next slide. So again, batch ensemble, this is trying to get the benefits of a full ensemble, but a little bit more efficiently. So we think of a full ensemble, right? For some layer, maybe a dense layer with weights W multiplied by some inputs. In a full ensemble or a deep ensemble, you'd have K copies of that weight matrix if you want an ensemble of K members. And so this works great. You get great accuracy, but it does explode the size of your model by a factor of K. So in batch ensemble, what we do instead is we have one weight matrix W in some layer, and then we'll introduce 2 additional weight vectors, S and R. And then instead of ensembling on the big weight matrix, we'll ensemble on the smaller vectors. And then there's a way you can show that you can vectorize the overall computation to get K predictions for each example. But again, when you do this, if you look at the parameter count for a single model versus the parameter count in a batch ensemble model, depending on the architecture, you might see something like only a 2% increase in the parameter count. So this is known as batch ensemble. All right, and then the second piece we said, the second extension is this idea of a Gaussian process last layer. So here, if you have some model that the last layer is maybe some dense layer that outputs logits, we're going to replace that with a drop-in replacement Gaussian process last layer. And the goal kind of here is if we look at this chart on or this figure on the far left, maybe we have like 2 classes that models been trained on, this kind of like blue upper arc and this orange lower arc. And those are 2 classes the model is trained on. Let's say it was trained well. But then this third little clump that's in red at the bottom shows up at eval time. So if we go to the far upper right, this maybe is like the decision boundary for a normal model, where it might place a boundary between the upper and bottom arcs to separate the 2 classes. And this works great if your model is going to be evaled on the same distribution it was trained on. But then, like I said, you have this like third class at the bottom that's shown up at eval time. It's some other class, but a normal model might classify that confidently as class 2 or this lower orange arc. Whereas what we really want is the bottom right figure where the model still separates them, but it is only confident in the region around the original classes, the blue and orange arcs, but not confident around this new third class. And so this Gaussian process last layer gives us that ability. And if you're familiar with the SMGP paper, the original paper had a spectral normalization layer on the model. We find for large pre-trained models, you just need the Gaussian process. And I want to point out while I'm here too, this and batch ensemble and the next one, we have drop-in replacements for these. So we've got them both in TensorFlow with Keras layers or in JAX with Flax layers. And let's go into the last one. So the last extension that we can use is another last layer method. So again, replace the last dense layer with in this case, a heteroscedastic dense layer. And what this just does is allows you to get noise estimates that are also a function of the inputs. So not just the mean, but also noise of it. For like a softmax type of setup, it would allow us to like sample from a Gaussian over the logits. And we just see this, it results in better calibrated estimates of the uncertainty. And so if we come like to the ends, like what are the final models that we look at? So we have, again, vision and text. So for vision, it's, like I said, a vision transformer, size large. We're going to pre-train this with this batch ensemble. As a detail, we'll only put batch ensemble in the last few layers, and we'll find like you get most of the benefits with the least amount of additional compute. So we'll always pre-train with batch ensemble. When we fine-tune it on downstream data sets, we'll keep the batch ensemble there, but we'll also replace that last layer with a heteroscedastic last layer. And that is our final VIT Plex model. And for text, we're always going to start with a T5 pre-trained model, just a regular one upstream, particularly a 1.1 large. And then we're going to fine tune that with batch ensemble on the last few layers again, and then with the last layer replaced with the Gaussian process last layer. So these are be our final models, VIT Plex and T5 Plex. All right, so with that, I'm going to pass it over to Jeremiah to talk about results for these models and the tasks we just talked about.
All right, thanks, Mike. So yeah, so now we're going to take a look at the result we got from these models. And the first slide we saw here is a radar plot summarizing the performance of the vision and the text models that Mike just introduced on different tasks. So what you can see is, for example, if we see the figure on the left, on each specific axis is a performance for a specific task. And then the performance of the Plex model is essentially highlighted in blue, and the best performance that we collected from the literature is in red. And to highlight the impact of the size of the model architecture, especially on the tech side, we also showed the performance of the Plex model based on the base rather than large architecture. That's on white. So in general, what you can see is using uncertainty methods on top of the large pre-trained models, we essentially see a very roundabout performance across all different kind of tasks. Well, if you see the previous state of art, it is either significantly underperforming, uh, yeah, and in some rare cases that it's outperforming, but usually those are based on very specialized techniques. So one example is, for example, on the text side, we can see for the accuracy on the very top, for the natural language inference, for the subpopulation shift, that performance is achieved by synthetically generating additional data that specifically targets the model weakness and add those to the training data set. In comparison, the Plex model is just working rather well out of the box. And the other point you can see is the architecture does have a impact on model performance. This is highlighted by, for example, on the text performance on the right, the the convex hull encapsulated by the Plex large is completely contains the performance of the Plex base model. Next slide, please. Yeah, and then so here are some highlights of the new capacities for the large language model that we can unlock using this using the Plex model. So the first thing we see here is selective prediction. Essentially, this task is about if the model, given a example to make prediction about, if the model is highly uncertain, it can just refuse to do prediction. In this way, we prevent the model from generating overconfident predictions. And what we see here is a performance plot of X is review fraction, meaning the maximum of percentage of the data we allow the model to abstain. And on the y-axis is a collaborative AUC. That is essentially we compute the overall AUC, but with the expert, with the percentage of abstain example being flipped to correct, as if the model handed this prediction to human expert and asked them to give correct prediction. So the selective prediction performance is a combination of a model's ability in uncertainty quantification and also in original predictive accuracy. And what we can see is compared to the baseline model, right, the Plex model have a significant up to 10% boost in selective prediction, especially when the review fraction is small, meaning the model is only allowed to defer a tiny amount of examples to human expert. Next slide, please. Yeah, and here is another task that we are able to unlock with the Plex model. So this is a structured open set recognition, which is coming from the NALU task that Mike mentioned earlier. So just a reminder that this task is essentially imagine that we're building a chatbot. Given a user query, we can predict not only the specific intent the user is asking for, we can also predict the domain and the vertical, right? In this case, it actually unlocks some interesting ability for model to partially quantify its uncertainty. Meaning, for example, if we see the example on the top, the user is asking to change the password to the bank account. There might be the case that, right, like our service, we do have a bank service, and we do have account related service on our bank, but we don't have this specific functionality called change the password of a bank account, right? So in the older days, if you only have a atomic intent prediction, maybe you just have to punt outright, which does leads to a unpleasant user experience. And in our case, if you can partially recognize, oh, this user is asking about something about a bank account, right? You can using this information to produce more tailored clarification, asking questions to continue the dialogue. For example, here the body is able to say, we don't specific support this action. Do you want to call, say, customer or service for the bank account app? Next slide, please. Yeah, and here is an additional another ability that we can unlock with the Plex model, which essentially is a zero-shot open site recognition. So what we are highlighting here is for very challenging auto prediction examples, the model can still perform rather robustly. What you can see here is, if you see here, there are 3 columns of examples, where on the bottom row are training examples, examples in the training data, and on the top examples are very hard out of the wing examples that are not in the training data. And the model is supposed to detect reliably that these are the kind of examples you have never seen before. So these examples are actually rather challenging for neural network models, because if you squint your eyes, right, like in terms of high level structure of the image or the tones of color, they actually look rather similar. So what we discovered is the Plex model actually can detect these very challenging and so-called near OOD examples rather well. Next slide, please. Yeah, and the next is about the label uncertainty, which is about the fact that a lot of examples that we encounter in the real world is actually either ambiguous, in the sense that if we ask multiple raters to rate them, there will be rater disagreement, either because the image itself is incomplete, blurry, or because it just contains multiple attributes. And what we see here is the Plex model, especially built on top of the heterostochastic layer that Mike introduced earlier for the vision set. It can capture this kind of ambiguity rather well. And next slide, please. Yeah, and finally, we also see a significant improvement in the active learning, in the sense that if we perform active learning using the uncertainty from the Plex model versus baseline, we do see a significant improvement, in this case up to 40% when in the low sample regimes. Next slide, please. Yeah. So after looking at those performance highlights, here are some high-level take-home message that we observed. The first one is the performance, the general reliability performance of the model actually scales almost linearly with respect to model size. So what you see here is a x-axis, which is the overall compute days needed to train a model, and the y-axis is so-called reliability score, which is actually computed by aggregating all the performance metrics that across all different tasks that Dustin introduced earlier. Right, yeah, so in this specific case, it will be aggregating 139, accuracy, selective prediction, auto-domain detection, calibration, etc. scores for vision, and 54 for language. And what you can see here is as the model complexity and model size increases, you do see a robust increase in reliability score. Next slide, please. Yeah, and the second axis that we look at is, say, assume we experiment on different kind of uncertainty models. How does Plex perform? And here, x-axis will be different uncertainty methods, and the y-axis are ranking performance of these methods across different tasks. So you can see that, for example, yeah, so like the lower, the better, essentially. So we're comparing Plex, which is a batch ensemble plus a heterostochastic or GP, versus other simpler model variants, which will be, for example, batch ensemble only, that will be the BE, only with the heterostochastic layer, or like the non to GP is saying if we just pre-train, we take a deterministically pre-trained checkpoint and we put the GP on top of the model at fine-tune time, or just like making no changes at all. So what we see is aggregating all tasks, the Plex model consistently is ranked highest among all the other variants. Next slide, please. Yeah, and finally, this is one striking and very interesting observation. That is, we actually observed a strong correlation between the pre-training performance in terms of the validation negative log likelihood and the model's general performance in the downstream fine-tuning tasks. And what the plot you're seeing here is x-axis are different performance scores, and the y-axis is the correlation between the pre-training validation negative log likelihood with these downstream performance, measuring across different tasks. For example, we can see that on the very right of the figure, the Breyer score and the AUROC and also few shot accuracy and the selective prediction. These also all have a rather high correlation with the upstream pre-training performance. And then in comparison, the more standard performance metric like negative log likelihood and accuracy have a moderate correlation, while the more uncertainty targeted metrics such as expected calibration error, which is the ECE, and also the calibration AUC, those correlation are rather low. Yeah. Next slide, please. Right.
Okay, and I'll take it away. We also spent, so that sort of covers sort of like our main highlights for results. Happy to chat more about them, sort of their questions. We also sort of open sourced pretty much all of our code. That includes training, eval, all the configs, the checkpoints, and there's a bunch of different individual layer implementations. If you just care about like, taking specific parts of our overarching recipe. And just sort of as a take-home message to sort of wrap up the presentation, first we sort of thought about what is reliability, how do we get models that are a bit more safe, that understand exactly when they shouldn't make specific predictions, or this overarching sort of framework. And we sort of targeted, hey, what are these key ideas to get sort of a simple recipe to work well across these sort of reliability sort of benchmarking. And in terms of resources, definitely check these out. Thanks. Happy to take questions.
Okay, hi. We still don't have questions here in our Q&A, and so for everyone in the audience, okay, now I have a question. Perfect. So yeah, for people in the audience, if you want to ask a question, go to the Q&A, not to the normal chat feature, go to the Q&A. Okay, so our first question is from David. What were other methods or approaches you tried that didn't work as well as these three extensions?
I can probably take a stab at that one first. I think the thing that we most experimented with was exactly how to do efficient ensembling. So this is also partly covered in some revelations in the paper. So we try things like MIMO. So this is sort of like ensemble that's sort of efficient also not only for parameter efficiency, and like memory, but also inference time, so like runtime. We also just tried like a bunch of different like types of like deep ensembles, so like just ensembling a bunch of different checkpoints. I think one of the key difficulties is that if you're trying to ensemble both for pre-training and fine-tuning, and that's sort of important because you sort of see benefits in both sides of it, it's very hard to like, it can be very hard to make gains that are trying to minimize the total runtime to actually train these models. So it's mostly in the space of efficient ensembles. MC dropout was another one that we experimented with.
Okay, got it. While we wait for other questions, in that plot comparing the ablation plot where you had like full Plex and then you had no addition, you had yeah, that one. Okay, so if you go to the language part, we see that non-large is doing like pretty well compared to, for example, Plex base. And so my question is, how much do you think this is another situation where, you know, just scaling up the models, you can pretty much get the same improvements in the many uncertainty metrics as you get from, you know, using the special stuff in Plex?
Jeremiah, do you want to take with that one? I go next.
Yeah. So, well, actually, if you look at the non-L performance versus Plex L performance in detail, right? What you'll see is the performance is actually pretty polarized in the sense that in some situations works really well, right? You see some in the bottom 1 or 2, and in some situations really bad, right? You see the 6 and 7, and there's a lot at the 7th place. So what we see there actually is when your sample size is not that large, or you start to have bias either in the label or in your data distribution, right? For example, if you are dealing with, say, toxic comments that you have a lot of negative examples versus a few positive examples, or in the case that you are dealing with spurious correlation and subpopulation shift, in this kind of situations, we do see that uncertainty models helps a lot. And in comparison, the vanilla methods doesn't work as well. Yeah. And the other thing is, so the other possible thing that you see sometimes in the non-large is doing well is we're looking at a whole collection of metrics. We look at accuracy, we look at purely uncertainty, we look at selective prediction. So accuracy and selective prediction sometimes, you know, like these are metrics is a blend of both uncertainty and accuracy. So if the non, you know, like is doing well only prediction wise, it can still, you know, have a higher ranking in a subset of tasks.
Got it. Thank you very much. So another question now from Charles London. Do you have advice on when the GP layer or heteroschedatic layer works better to improve uncertainty estimates? So basically when to use one versus the other.
I would say they sort of do different things. One is about trying to capture sort of the amount of noise that sort of appears in like different output classes or like different sets of tokens or language. There are ways to, and GP is sort of like it's more about sort of like the metric that you're sort of like looking at when you compare like a given sort of input relative to another sort of input in sort of this overarching embedding space. There are ways to combine them. So there's a paper that some of us did, our team, to exactly combine sort of heteroscedastic and GP layers. We didn't try that too much in Plex yet. But yeah, there's certainly ways to do a bit more on both of them.
Can you please explain a bit more about heteroscedastic? in the context of text or NLP?
I can take this one. Implementation-wise, it's just putting the header stochastic layer on top of the last layer, and in terms of interpretation of these methods in the context text, it will be there are cases that for a specific type of input, you will have stronger likelihood of seeing label noise versus some other situations. Like coming back to the text toxic comment example, let's say, there are cases that when the topic itself is leaning political, you will see a higher disagreement among raters, for example. Hence, you will see a larger amount of label noise. And yeah, similar situation applies to, say, natural language understanding. Sometimes you do see noisy-ish utterances that leads to ambiguity in your final labels. Yeah, in those cases, the stochasticity is a good inductive bias that we want to impose to the models.
Thank you very much. What did the process for coming up with your characterization of reliability look like?
I can probably start with taking that one. So I guess what we did was sort of like on one side, we try to ground a bunch of different, so for, there are many different facets of this. So on one side, when we think about like different things around how to think about uncertainty, so you have to actually sort of ground these in, realizable metrics where like lower is better or higher is better. And, there's a perfect sort of like model that you try to capture to get to that sort of level. And most of the time, when you look at sort of uncertainty metrics in literature, they're very sort of academic and they're like specifically doing like calibration error. So what we did was like think about more broadly, how are all these sort of models being used in downstream production? Like how are they used in specific applications? And then how are they actually measured? It's usually not just looking at, whether my probability estimate aligns with my accuracy. So most of the metrics that we were thinking about sort of are like the decision-making scenarios that involve a lot of these qualities implicitly or explicitly. So for uncertainty, one of them that was super important was selective prediction, which Jeremiah was just talking about, where you're using the uncertainty as part of getting better or more accurate predictions. But yeah, a lot of it is about talking to folks to see like what they actually use in practice.
Thank you very much. So you tested on VIT, and on T5. So both of them were transformers. Why was that? If I try this on like a ResNet 50, should it also work, or do you think there would be some kind of limitation there?
I can take a stab at this. Yeah, so I think like with transformers, part of that is just following like recent literature of seeing continual gains with like scaling up transformer architectures. But like for your question of like, would it work for other ones? I think this is one of the nice things about these different methods. So I talk about batch ensemble and SMGP and heteroscedastic, right? Like, these have been refined and have been worked on across different data sets and different types of models in the past. So, batch ensemble, we've seen this work well for originally on like ResNet 50 style models. We've seen it work for like custom LSTM based models. And now like, of course, onto transformers. And so like, there's like this nice history, I think, for each of these, like saying like, they work well across different architectures, and we have like implementations for that. So maybe as a plug, like within the code base that Plex lives in, like we have a broader set of baselines. And for some of these other types of architectures, we have those for batch ensemble and SMGP and so forth. So in this paper, we did try to limit it. I think partially because, like I said, following recent literature and staying there, but also like the scope of what we wanted to do of doing these like huge ablations, like this plot we're looking at, boils down, I think, a very large number of experiments of like combining all these different pieces together. And certainly you could expand this to the architecture as well. But I think for within the scope, we limit it to transformers here.
Yeah, I think transformer is just a simple thing. People tend to use it a lot. And this is sort of like a year and a half in the making. So we really, have to consolidate on one specific choice early on. I think if we were going to like redo this sort of now, it would probably be like going maybe even more ambitious, which is like not just these two models, T5 Plex and BitPlex, but a multimodal model that can do both language and vision jointly. And like right now, I think our model sizes are like almost peanuts these days. They're only up to like a billion parameters. It's sort of like obvious how like you can think about taking these approaches and then going to the crazy, Palm Lambda sizes.
Cool. It makes a lot of sense. Yeah. Okay. We have two extra questions, but I'll ask one from myself before it. So as you said, like it's been 1.5 years in the making, and there were quite there were many authors, and there were authors from Google and University of Oxford. How was coordinating all of that? Do you have any tips for coordinating collaborations of this kind of size?
I can take a stab at that first. I think one big thing we've actually found in this paper, but also like some previous work as well, is being able to center a group around like one large, nice code base. And this was particularly nice for external collaborators in that vast majority of our work is open source by default. It's open source first, and we develop it in open source. So for the collaborators at Oxford, right? I mean, we would jointly work on CLs together, and that would get pushed to GitHub. And whether we had it internally running or they were running it, I think we've seen this across multiple works that pulling together a large group is helpful when you have like a shared code base that you can iterate on and share. I think that's like one big aspect that I think we definitely found like to be quite helpful.
Yeah, definitely +1 to the code base. It kept us probably the most grounded because it was like the key, like that's the most materialistic thing that we actually were consolidated on. But yeah, there's so many different challenges, and organizing a large effort that is like very different from your typical sort of like grad student paper or like one-off sort of industry lab paper that involves like 5 authors. There's like many different sort of modalities. There's politics involved. There's thinking about just sort of like how do different hierarchies of sort of contributions work, who sort of leads individual sections. I'm happy to go into. I can give a talk just about like organizational challenges.
Okay, thank you. And yeah, that talk would be interesting. Okay, so the next question is from Charles again. What do you think is the main reason for accuracy improvements when not referring to an expert? I understand that these extensions should lead to better uncertainty estimates, but why do they improve results when the model has to select a class, even if it's very uncertain?
I can start to take a stab at this. Like, so for at least like for one of the extensions, Batch Ensemble, this is based on trying to get the benefits of full ensembles. And there, I think, especially as maybe opposed to SMTP and heteroscedastic, like we find with ensembles or efficient ensembles, like improvements on uncertainty for sure, like improvements on calibration, et cetera. But we also find improvements on accuracy, and a lot of that goes back to just getting some approximation, like marginalizing over some space of models. So I think the accuracy improvements are expected. We would expect that a priori with the batch ensemble extension.
Yeah, I think ensembling always helps. It's sort of like the magic trick behind all machine learning. I think like if you try to think about it from like a mathematical perspective, it's really about how do I make a good prediction that involves this high dimensional integral. It's this integral that is over all the things that I'm uncertain about. It's all the random variables. And that's exactly what the uncertainty aspects are targeting. It's not just targeting better calibration, but it's targeting decision-making under that interval.
Thank you very much. And now another question from David. Are there big extensions or uncertainties, no pun intended, you or others are looking into?
Okay, I can take a stab at this one. So I think the thing that I'm most excited about is trying to simulate a lot of these ideas just more into sort of like bigger architectures and bigger models where there's maybe more sort of emergent capabilities. So I think like Palm/Lambda style models where you're thinking about reliability in sort of like a chat or dialogue based perspective. I think that's also super interesting. One area that we sort of moved a lot toward after Plex has been sort of like structured levels of uncertainty. So Jeremiah was talking a little bit about this with sort of this open set recognition problem where you don't just say, hey, I don't know how to make a given, I can't answer your query. It's, hey, I recognize this part of your input. Let's clarify this aspect so I can actually assist and give you that problem, give you that answer. I think there's all different aspects of sort of structure there. And one of them we're also investigating is like structure and sort of dense vision tasks. So can I recognize unfamiliar object in an image? If I try to sort of understand the given scene in an image, can I detect the different parts that are known and unknown? How do I leverage that in the overarching like self-driving car system or, just sort of a traffic sort of street system?
Okay, thanks a lot. There are no more questions at the moment. Let's say just a little bit, but we're almost at time. So
yeah, thanks for all the different questions.
Yeah, no, it's been great. Yeah, it's a really cool paper, and it makes you think about lots of ideas. Yeah. Okay, I think given that the next question was a thank you, I think we can close on this. So thank you very much for giving the talk, and looking forward to the new stuff we're going to be doing.
Cool.
Yeah, thanks for having us.
Thanks.